can we visualize boiling at the molecular level? Have you ever wondered what happens to water when it boils? Can we actually see the magic unfold at the tiniest level? Let's break it down. Boiling is not just a simple process of water turning into steam. It is a fascinating phase change where liquid transforms into vapor when heated to a specific temperature known as the boiling point. At the molecular level, this involves water molecules gaining energy. They move faster and eventually break free from the liquid state to form vapor bubbles. So, how do scientists visualize this process? One effective method is through molecular dynamic simulations. These computer-based models simulate the behavior of individual molecules using the laws of physics. For instance, researchers can see how vapor bubbles begin to form at certain spots on surfaces. This is influenced by whether the surface attracts or repels water molecules. Surfaces that attract water are called hydrophilic, while those that repel it are hydrophobic. These simulations provide a detailed view of how tiny vapor cavities form and grow into bubbles. This is something that is hard to capture with regular experiments. On the experimental side, high-speed cameras paired with specially designed heated surfaces allow scientists to observe the formation and growth of bubbles on a microscopic level. While these cameras do not capture individual molecules, they show the dynamics of boiling bubbles and how thin liquid films behave on surfaces. This information is directly related to the interactions and energy changes happening at the molecular level. Additionally, there are software tools that create three-dimensional models of molecular structures and interactions. These programs help us visualize how the shape of molecules and the forces between them affect boiling points and phase changes. For example, as temperature rises, molecules move further apart, overcoming forces like van der Waals interactions. Understanding boiling at this level is not just for curiosity. It has practical applications. For instance, it can help improve heat transfer in cooling systems, design better thermal barrier coatings, and optimize industrial processes that rely on controlled boiling. By combining molecular simulations with experimental observations, scientists can create more efficient systems and materials. While we cannot see individual molecules boiling with our eyes, advanced techniques like molecular dynamic simulations and high-speed imaging give us a clearer picture of the boiling process at the molecular and microscopic scales. These methods make the principles of thermodynamics easier to grasp by connecting molecular behavior to what we observe when boiling occurs.